Hello all. I wanted to go through this video, Factors Affecting Solubility Rate, since I won't be here Monday. And I'll also explain the two assignments that are going to be due today as well. So let's dive in and get started. This one shouldn't be as long as the last one. So when we talk about factors affecting solubility rates, really we're talking about trying to increase the solubility in something, or more specifically, trying to make more dissolve into something else. We're going to specifically talk about gases dissolving into liquids and solids dissolving into liquids. You can mix solids together. You got to heat them up and then let them cool back down after they're mixed. And gases will dissolve at each other as well, but we're talking more specifically about these two into liquids. Starting with solids, first off, we're going to increase temperature. So in order to get more solute dissolved into a solvent liquid, you would need to increase the temperature of that liquid. The particles have got to move faster, and the faster they are moving, the more they will come into contact with the solute, therefore taking it away with them and dissolving it into the solution. So those particles just have to move faster. This is why whenever you make sweet tea, you do it when it's hotter, right after you brew it, ideally, and you can dissolve more at that temperature than you can if you have iced tea and you just try to mix sugar with it. It'll never be as sweet as sweet tea. So we increase temperature to increase solubility. So here's a picture of cold water with a little sugar cube, and then hot water with the same size sugar cube, and you can see it's already dissolved a lot. Usually you only see sugar cubes being put into like things like hot tea. Because it's hot, it'll dissolve faster. Usually to put sugar into something colder, it's broken down, and we'll talk about that next, actually. This graph shows the effect of temperature down here at the bottom in Celsius on solubility, which is essentially grams dissolved into water. And so as you go up in solubility, all of the graphs or the lines, curves, increase as they go to the right as well. So this shows you that all of these at least increase in solubility as you increase temperature. There are always exceptions. Some graphs have a line, kind of looks like the salt line, but it's slightly going down. There are a few things that will decrease as you increase temperature, but overall, the increase they increase in solubility as they increase in temperature. Another way to increase solubility is to agitate the solution. And this is either stirring or shaking. So whenever usually you see people trying to sweeten their tea, they stir it with a little teaspoon. This just allows more of the solvent to come into contact with the solute. So it just increases that likelihood of contact collisions in order to dissolve. Shaking does the same thing. I think of people putting like protein powder or things like that into liquid and see it on the top and shaking it up. Does the same basic thing as stirring. It just increases those likelihoods of collisions between the solute and the solvent. And then final one that we're talking about with solids, at least, is to increase the surface area. So breaking it into smaller pieces, chunks, powders, things like that. If it's the smaller it is, the more surface area there is to come into contact with the solvent. If you have a sugar cube or just a big chunk of some solid you're trying to dissolve, it's going to take a lot longer because only the surface of that at any given time will come into contact with the solvent. So it's going to take longer for the parts in the center of that big chunk to finally get to contact the solvent and dissolve away. So if you break it down into smaller pieces, it will dissolve faster. Here you have a solid that's a few layers of atoms thick, but only this surface layer will actually come into contact with the solvent, these water molecules. So these guys that are up here, deeper inside the chunk of solid, whatever it happens to be, won't come into contact with the water until all these on top of it are gone. So what we do is we break it apart. So here's a sugar cube that was colored with a Sharpie red, and another one that was colored but then broken apart. And you can distinctly see the red where that would have been the surface before, and all the white is extra surface now that the solute could come into contact with the solvent. So the more white in this case, the more surface area there would be over just the one that's red. So breaking it, crushing it, grinding it down, all these will affect solubility. Here's just another depiction of the same basic thing. You have a solid chunk over here, and these yellow things represent the solvent, and so it could only possibly contact these on the surface. These in the middle would have to wait until the others were dissolved. Here you have these that are already broken up, and more can come into contact with it at any given time. Give me 1 second. Hey guys, sorry about that. I had to take a little break. Somebody needed something. So you break it up, more will come into contact, allowing more to dissolve faster, and that's the overall goal. Switching gears a little bit, we'll go to solubility of a gas into a liquid. So think of the carbon dioxide dissolved into your Coke. Ideally, you want more carbon dioxide dissolved in there so that it tastes better. A lot of that Coke's taste, the slight bitterness of the carbon dioxide is key in that taste. And if all that gas escapes, then it's going to taste what we call flat, but essentially it should taste different. So with a gas, to increase the solubility of it, you actually decrease the temperature. You make it colder. So what that does is those particles are moving at a certain speed, and as you make them colder, they move less. And so moving less allows less availability or less opportunity for those gases to kind of wiggle their way out. Compare it to you trying to walk down a crowded hallway. If everybody's moving, you can kind of move in and out through the people a lot easier. But if everybody was just standing still and you had to move through, it would be a lot more difficult to get around people to move through the hallway. So this is the same basic thing. The more those particles are moving, the more gas escapes. So solubility would go down. In order to increase solubility, you make it colder so those particles stay moving less to hold in those gases. And you can see by this graph, it's just the opposite of that last one. As you increase temperature down on the bottom, solubility actually goes down. So gases act oppositely with temperature change than solids do. Pressure, you can affect pressure, or pressure will affect solubility. If you increase the pressure, this is essentially holding in the gases into the liquid. So the more pressure you add, the more gases will dissolve into the liquid. This is why a lot of bottling companies will add a little bit of carbon dioxide right as they are sealing whatever container it's in. And whenever you open it, that is, pressure escapes. And ideally, a lot of that CO2 is still in the Coke, and the taste is as you expect it and as the creators expect it to be. If all of it escaped and there was no pressure in there, it was allowed to just freely roam in the atmosphere, then the Coke would get flat and it would taste different. So it is the most carbonated right before you open it. So just kind of another depiction of the pressure thing. This guy is trying to push the gas particle into the liquid particles that are right next to each other. So the more pressure he applies, the more would stay into the liquid. So the idea of it overall is to keep these gas particles dissolved in the liquid so that the taste in the Coke's case is the same. Some other kind of real world things is in a lake. If global warming, various reasons, lakes and bodies of water can increase in temperature. If it does, those gases that are in the lake will escape, and things like fish depend on those gases. They breathe in oxygen just like we do, just kind of a different way, but they need that oxygen. And so oxygen is dissolved in the lake or the river, and if water is too hot, that oxygen can escape out, and therefore it's not in the water for the fish to breathe. So things like nuclear plants, power plants, a lot of times are built near water so that they can cool down their reactors with that water. If the water is immediately put back into the body of water they got it from, the river or the lake, then it's going to increase that overall temperature of the water, therefore allowing oxygen to escape, and a lot of the life will die in that body of water. So now it's very highly regulated. They have to let that water cool back down to a certain point in relation to the temperature of that body of water before they can put that water back in to where they got. In a Coke can, you can kind of see these CO2 particles are moving around. They're in there, they're dissolved, but as you open it up, they start to kind of come together, much like water would. They attach to each other, that cohesion stuff. And then as the bubbles get bigger, they rise to the top because they're less dense, and then they go out of the solution. The more those particles are moving around, the more likely they are to come together and come out of the solution. So this is why it's better to keep your drinks colder. More of that CO2 stays in there, and they're going to taste a little better, or at least as the company desires them to taste. One important note, we didn't talk about pressure with solids. Pressure has no effect on the solubility of solids. So you can add as much or take away as much pressure around the liquid when you're trying to dissolve a solute in it that's solid, and it's not going to affect it in any way up or down. So pressure doesn't affect solids. Pressure will affect gases. I wanted to show you also the couple of assignments that you're going to be assigned with this stuff. Sorry, that's kind of a freaky little thing there. So the first one is called unsaturated, saturated, and supersaturated. This one's going to use that graph of solids into liquids that we had. If I can get it to pull up. I believe this one is 15 questions, and it's going to use this graph on every question. And just like the others, 3 attempts possible, it will build. So for your second and third, you should only have to do the ones that are that you missed on the first attempt. And so they'll all kind of look like this. This will only be on the first one with the graph, but all of them will be like this. Give you kind of a hint over here, if you will. For a solution to be saturated, the point that it gives you needs to be on the line. If the point is above the line, we call it supersaturated. And if the point is below the line, it is unsaturated. So here I have 150 grams of Ki at 20 degrees Celsius. So you find your line. Ki is this one right here. I'm looking at 150 grams, which is this very top part, at 20 degrees Celsius, so down here. So I go up the 20 line till I get to the 150 line, and it would be right here, and that is above the line, so I would say that is super saturated. If it was right on the line, I would say it would be saturated. That would be about 145 at 20 degrees Celsius. And if it was below the line, that would be unsaturated. So I'll show you one more, and then we'll move on to the other assignment. So this one, 130 grams of Ki at 10 degrees Celsius. So here's 130. This first vertical line is 10, and so that is below the Ki line. So because it's below, I would choose unsaturated for that one. So the lines will be different, so make sure you see which compound it is. These instructions are all the same for everyone, but the compound will be different, and then the amount of grams and the temperature will be different for all of them. So you're just comparing them. And remember, if it's on the line, it's saturated. If it's above the line, it's supersaturated. And if it's below the line, it is unsaturated. We'll go back and show the other one. The other one is this one called dissolving. And this one takes into account the PowerPoint that we just went over, all the factors affecting solubility. Same parameters for all of this. But you'll just be asked questions in a bunch of different ways of how you could increase or decrease solubility of whatever it's asking about. So your first option here, over here, I gave you, I misspelled that. That's sold. It should say solids. If you, to increase it, you increase the temperature, you agitate it, or you increase surface area. For gases, it's a temperature decrease and a pressure increase. So make sure you get the differences between those. So here's one question: which of the following will speed up the dissolving of a solid solute in water? So increasing solid in water. So to increase it, we either increase temperature, we agitate it, or increase surface area. And so freeze the solute, that's making it colder. Stir the solution, that's agitation. Grind up the solvent, that would be like you're grinding up the water. It doesn't work that way. And then cool the solution, that would decrease solubility. You want it hotter. So stirring is the best answer there. Another example, increasing the surface area of a solid. So that will increase solubility. causes it to ionize. That's something way off. Speeds the rate of solution